chapter 9. Today I'm going to cover 9.3. Alright, 9.3, the integral test and pre-series. Alright, let's go to the first theorem, theorem 9.10, the integral test. If f is positive, continuous, and decreasing for all x greater than or equal to 1. So make sure you test all the three conditions here, that f is positive, is continuous, and decreasing. And a sub n equal to f sub n, then sigma n from 1 to infinity, a sub n, and an integral of the function from 1 to infinity, either both diverges or both converges. Alright, so let's look at the first example. I have a series of this summation from 1 to infinity, 2 over 3n plus 5. So I'm just going to call 2 over 3n plus 5 as a function f of x. Alright, as you can see, if n is positive, you're going to have positive function, right? And it's continue because you don't have 0 on the denominator regardless what is n, and we don't have radical root here. So two conditions satisfied: positive, continuous for all x greater than 1. So I'm satisfied the first two conditions. Alright, I have to check that it's decreasing. I have to check that this function is decreasing. And the way to check this, I'm gonna take derivative, and if the derivative greater than 0 is increasing, if it less than 0 is decreasing. Okay, let's look at the function. F of x is equal to 2 over 3x plus 5. I choose to do quotient rule. Alright, so is take derivative is denominator times derivative of numerator minus numerator. Derivative of denominator is just 3, right? And divide by denominator square. I simplify the numerator. I have negative 6 over 3x plus 5 quantity square. As x greater than or equal to 1, our denominators, because it's square, it's always going to be positive. Numerator is negative, so the whole thing is negative. So it's decreasing. So I did test positive, continuous, decreasing. Then I can apply the theorem. If these three conditions does not satisfy, you cannot apply the theorem, right? So what the theorem said, that I have this summation and I have a function. Instead of find the convergence or the divergence of this, I'm going to find convergence or divergence of a function as an integral from 1 to infinity, as you can see here. Alright, so I have a function here, an integral from 1 to infinity. The next step, what I did, I pull out the 2, because 2 is constant. I can take it out. Alright, and from here I'm going to apply this theorem here, or this rule here. I have my u is 3x plus 5. Derivative of this is 3. So I'm missing the 3. Alright, I'm going to force it to make it perfect. So I'm going to write the 3 here and divide by 3, which is the same function here. Alright, so I have 2 over 3, an integral from 1 to infinity, 3 over 3x plus 5. Because it's improper integral, I'm going to take a limit as b go to infinity, an integral from 1 to b of a function 3 over 3x plus 5 dx. Alright, next step, 2 over 3, just 2 over 3, limit b to infinity is just that, and I apply this definition here. I end up with ln parenthesis 3x plus 5. The upper bound is b, the lower bound is 1. Alright, now I substitute b for the upper bound, alright, and I substitute 1 for the lower bound, so it's 3 plus 5, which is 8. Now as you look at limit as b go to infinity, this whole thing will go to infinity. Minus ln 8, which is some number, still you're going to end up with infinity, which is diverges. As the theorem said, they both have to be either both converges or diverges. Since I proved that this is diverges, so our original sum would be diverges as well from theorem 9.10. Alright, see you next example. Hi, let's look at the second example. Second example, the question giving you some summation of fraction 1/3 plus 1/5 plus 1/7 plus 1/9, and if you want to see if it converges or diverges, right? So first thing you have to do, you have to convert it to a series, right? Look at the numerator, it's all 1. So I'm going to have 1 on the numerator. Denominator, I have 3, 5, 7, 9, 11. So it's odd, but it doesn't start from 1, it starts from 3. So I'm going to do 2n plus 1, because if my n is 1, I'm going to have 3. My n is 2, I'm going to have 5, and so on. Alright? So this is my series. And I set this equal to f of x. Alright? As you can see, it's positive, because n start from 1. You're going to have positive. And it's continuous. We don't have a 0 on the denominator. Now we have to check for decreasing. It's positive, it's continuous. We have to check for decreasing. So I rewrite it a little bit here, alright? And I take derivative. The -1 go up front. -1 and -1 is -2, but I have 2x. So the derivative inside is 2. And I rewrite this as -2 over 2x plus 1 quantity square. Denominator is square, so it's positive. I have -2, so the whole thing is negative for all x greater than or equal to 1. So it's decreasing. Alright, so we can use the integral test. Look at my function right here. 1 over 2x plus 1. I take an integral from 1 to infinity. I'm going to use this property again, integral of u of du. So the derivative of 2x is 2, so I'm missing the 2. I'm going to write the 2 and the 1/2, right? So the 1/2 is over here. Because we have an improper integral, I'm going to take limit as n go to infinity, as b go to infinity from 1 to b. 2 over 2x plus 1. By apply this property, I end up with this whole thing here. And then the next step, I substitute b for the upper bound. So I have ln to be plus 1 and 1 for x. So I have ln 3. Alright, as b go to infinity, the first term will be infinity. The second term will be some number, but we're going to get infinity. So it diverges. Again, from this theorem 9.10, we can conclude that this whole summation is diverges. Alright, let's look at the next example. Hi everyone, let's look at our third example. Alright, look at the third example. I have a sigma for n from 1 to infinity, of n plus 2, n plus 1. I'm trying to apply the theorem here, and I know that I have to take an integral of this function, which is going to be difficult. So what I did the long division, right? X plus 2 divided by x plus 1, so you multiply by 1, so you have x plus 1. Subtract, distribute the minus in, so the x cancel out and you're left with 1. So you can write this whole rational as 1 plus 1 over x plus 1. As x is greater than or equal to 1, you know this is positive and it's continuous. Alright? So it's positive, it's continuous. I have to check for decreasing. So I'm going to take derivative of f of x. So if I take derivative, this is 0, bring the -1, and the power will be -1 minus 1, which is -2. And then I rewrite it as a fraction. You can see that as x is greater than or equal to 1, this whole thing going to be negative, alright, because our denominator positive, numerator is negative, alright. So I take an integral of x plus 2 over x plus 1, but I'm rewrite as 1 and 1 over x plus 1. I have an improper integral here, 1 to infinity. So I'm going to take a limit as b go to infinity for both terms. Alright? And then if I take an integral of 1, I just have x. Integral of 1 over x plus 1, I just have ln x plus 1. And as limit of b go to infinity, I just have infinity plus infinity, which is infinity, which is diverges. So from theorem 9.10, I can conclude that this whole summation is also diverges. Alright, see you next. next video.